Welcome students. This video lecture we are going to talk about the wave equation in two dimension. So wave equation in two dimension. So as I told you in the last lecture we have seen how to solve the wave equation in two dimension. So let me write down the equation. It is essentially the so this is called the D'Alembertian. You guys already know that, right? We did this thing. So D'Alembertian of u that is defined by utt minus Laplacian of u. Yeah. So this Laplacian that is in two dimension. That is why the wave equation is two dimension. So the problem which we want to solve today, this is 0. Okay, in R2 times 0 infinity. Clear? And what does u do on the bound this thing initial the base t equals to 0, u at the point x comma 0, let's say, that is equals to some g of x, and u with respect to t at the point x comma 0, that is going to be h of x, right? So this is for x in R2, and of course t equals to 0, that is given to you, right? So u and u and ut is given like this, and of course I mean u satisfies the wave equation in the interior of the domain. Now the question which we want to discuss is this: we would like to find an explicit, so our aim is this, exactly like n equals to 3, aim is to find an explicit solution u, okay, in terms of g and h. Clear? In terms of g and h, whatever we did initially, for the three dimensional case, we are going to do it for a two dimensional case. The exact same, I mean not the exact same thing we are doing. I mean what I meant is the exact same kind of goal we have. Okay, so we want to find an explicit solution. Now if you remember, in two dimensional case we define in three dimensional case we define the u which is by a spherical mean, and then you define u delta, which is like t times u and all, r times u and all. Okay, so all of those we defined, and after that we have deduced the Kirchhoff's formula, right? Okay, but here we are not going to do something like that because it won't work here. Okay, it won't work here. So what will happen? We are going to use something called a Hadamard's method of descent. Okay. Okay, so basically we are going down. So as the name suggests, you realize what we are trying to do here. What we will do is, first thing first, we will think of this problem in R3. Do you understand? So here you see u, if you u depends on x1, x2 and t, right? This u, for this problem, let's say that problem is 1, the u depends on u, x1, x2, x3. Now you can think of this as a function in R3 cross 0 infinity. So basically u tilde, let's say it is like x1, x2, x3, t, and you define it like in such a way that it is independent of the third variable. So basically u, x1, x2 and t. Is this clear? Do you understand what I am saying? See, here in our case in 1, the u depends on two spatial variable. Of course time variable is there, that's you can't do anything about it. But the thing is, the spatial variable are two variables, x1 and x2. Now what we are doing, but we know how to work with wave equation in 3 dimension. Yes, what we are doing now is we are defining a new u tilde, which is like x1, x2, x3. So it depends on 3 variables and of course the time, that we are defining as a u which is independent of x3. Is it clear? So basically, I mean, we are defining it. We are defining a three-dimensional function. I mean, of course, the time I am not. I mean, ignoring right now. Okay, the three-dimensional function in terms of a two-dimensional function. Clear? Okay, and then what happens is you write the formula for three-dimensional wave equation, and then you go down, you descend to two dimension like this. Okay, so let us start with the thing. Okay, so assuming, of course, you see, I don't know whether there is a solution or not. We are assuming that there is a solution. Okay, so assuming u, which is in C2 of R2 times 0 infinity. Clear? So let's say this solves 1. Okay, this solves 1. What I will do is I will write it like this. Okay, now set u tilde, exactly what we just discussed, x1, x2, x3 and t. This I am going to set it to be u of x1, x2, t. Okay, what am I doing? Again, let me explain to you. See, I am assuming that there is a solution of 1. If there is a solution of 1, it will look like that, this, right? U of x1, x2, t. So this is some particular number. For a fixed x1, x2, t, there is a fixed number. So now I am defining a new function u tilde of x1, x2, x3, t. Yeah, three spatial dimension, which is independent of the third variable. So basically, that will be defined as the value which u takes at x1, x2, t. Okay, so what is u tilde at x1, x2, x3 and t? That is the exact same value what u takes at x1, x2 and t. That is what we are doing. So you said this. Now once you do that, then from 1, okay, I think we do not have to worry about it. I can safely write this thing here. U tilde tt minus Laplacian of u tilde, that is equals to 0 in R3 cross 0 infinity. Clear? Yes, that is true. And what is u tilde? This is equals to g tilde, and ut tilde is equals to h tilde on R3 cross t equals to 0, right? Where what is g tilde? Again the same thing. G tilde of x1, x2, x3, we are going to define it as g of x1, x2 and h tilde of x1, x2, x3, I am going to define it as h of x1, x2. See, here in our initial case, we were given what g and h is, right? Okay, so here of course this x is x1, x2. You do realize that x is in R2, right? So x, I am writing it. So here x is like x1 and x2. Clear? Okay, but now what I am doing here is this g and h is given. I am using that g and h. Okay, so to define a new g tilde and h tilde. Okay, and of course if you define u tilde, g tilde and h tilde like this, then this is true. Okay, let's call it 1, 2. Clear? So this is true. Okay, now if this is true, see, this is in 3 dimension. I know from our last video which we did, Kirchhoff's formula, what is the solution of this thing. So we'll write that down. So from Kirchhoff's formula, okay, so from Kirchhoff's formula, okay, what do we have? We have u of xt. Clear? U of xt, that is given by, I will write it like this, u tilde of x tilde comma t. Okay, where, so basically, okay, let me write here x tilde, I will write it as x1, x2 and 0 and x is x1 x2, x is x1 x2 I have already written, x tilde I will write it as x1 x2 0. So basically I will just take the third variable to be 0. Okay, so u of xt is u tilde of x tilde t tilde. Clear? Sorry, not t tilde, t is t is t. Yeah? So that now by Kirchhoff's formula, what do you have? You have something like this, right? It is del del t of t, the average of del b. Let me write it like this: tilde x tilde. I will explain. Yeah. So this is just a Kirchhoff's formula. S tilde plus t times. Let me write it and then I will explain. Del b bar x tilde t h tilde ds. Okay, so here see what is b tilde here. B tilde is the ball in R3 with center x tilde. Okay, so where b tilde, okay, x tilde t is the ball in R3, because we are doing it in 3 dimension, right? Ball with R3 with center x tilde, with center x tilde and t positive. Clear? I mean, I think this is very clear to you. This is from the Kirchhoff formula, right? G tilde H tilde is because, I mean, we have this, I mean, u restricted at t equals to 0 is G tilde H tilde. So I am just writing it down, plain and simple. Okay, right? And of course, what is ds? Sorry, here it is ds tilde. Okay, and of course, okay, let me write it here, ds tilde. Okay, this denotes the, this is very important. Okay, this denotes the two-dimensional, okay, surface measure, surface area, you can say. Okay, the unit surface area on del b tilde x tilde t. Clear? Okay, see now why am I not writing del b? Del b, you see, since I am doing it in 2 dimension, I want my b to be, I mean, we denote ball with b, right? So I want my ball to be in 2 dimension, right? So that is why this b is reserved for 2 dimension. Whenever I am writing b tilde, it is for 3 dimension. Clear? Okay, so del b tilde is basically the sphere, the surface, I mean, the surface. Okay, so that is del b tilde. Okay, and b tilde is whatever is inside, of course, into 3 dimension, in 3 dimension. Okay, in 3 dimension. Okay, so let us do this part. First of all, I want to calculate what this is. Yeah, so in the surface measure of del b tilde, okay, x tilde t g tilde ds tilde. Okay, what is this? So now, okay, first thing first, let us break it up. It is 1 by 4 pi t square, of course, right? Because the surface area of the ball in 3 dimension is this 1 by 4 pi t square, and then you have del b tilde of x tilde comma t g tilde ds tilde. Clear? That is fine. Okay, now what I am going to do is this. See, this g tilde is independent of the third variable. See, what am I saying? You see, x tilde is independent of third variable, right? It is independent of third variable, x tilde. Okay, so g tilde, this g tilde of x, right? Okay, so first of all, what I will do is I will just write it down in how can I say? I mean, let me put it in surface this thing integral formula, and then I will do it. Okay, so see here, what am I doing is this. This is on the surface of the sphere del b tilde x tilde t, right? So you can, if you can think of it something like this. Sphere, right? Surface of sphere, a small unit part of this. I mean, forgive my drawing, I am not very good at it, but anyway, so this is a part of a sphere. Okay, a small unit part, like let's say del b tilde, small part in 3 dimension sphere. Now you see what I will do is, I mean, of course this sphere, I mean, for z x3 equals to 0. Okay, for x3, so this is x1 x2 x3, x1 x2 x3. So for x3 equals to 0, so basically this the hemisphere. Okay, this is some part. Okay, I hope this you understand my drawing. Okay, so the base is x3 equals to 0, so this is for x3 equals to 0. Okay, now you see, if you project it on this, I mean on this part x3 equals to 0 here, if you project it, okay, it will be corresponding to some kind of rectangle or some region here in, let's say, D capital. Okay, so you understand what I'm trying to say. Okay, this is the surfaces, the small surfaces, and corresponding to that this D is there. Okay, if you project it in this 2 dimension. Okay, so what is the formula? Let's say this surface S. So let me write it, maybe I don't know how, maybe I can write it here. Yeah, maybe I can do it here. So I think you guys know this thing, but still let me write it. Yeah, so the surface integral, so let's say let the surface is given by z equals to I mean something, let's say p of xy, some function of x and y. So basically, I mean, it's a graph of some function. Sorry, z equals to p of xy. Yeah, so, I mean, let's say you have the surface which looks like z equals to p of xy. Okay, so then the surface integral, is given by, so you see, if the surface is given by the graph of this function z equals to p of xy, so graph of p, okay, then the surface integral, if you want, of some function f, let's say double integral over s, f of x y z ds. Okay, I am taking x1 x2 x3, so let me write it like x1 x2 x3. It will be, otherwise we may get confused. Okay, let me write it like that. So f of x1 x2 x3. Okay, so this is your s, and that's your d, right? So x1 x2 x3 with respect to ds. Yes, surface, this thing, this is double integral over d is the region here. Okay, f of x1 x2, and x3 is getting replaced by p of xy. Clear? P of xy. So here also I have to change this. Let me write it like this. x3 is p of x1 x2. Let's say that's your surface. Okay, so x3 is given by p of x1 x2, graph of some function p, and then I mean you can write it like this, and of course you have, due to this change of variable, you have this you know, the scaling. Yeah, so that is given by p x square plus p y square plus 1. Okay, and then you have the area element dA, right? Okay, so dA is basically, you know, dx1 dx2 dx3, that sort of thing. Yeah, okay, now so essentially you see I have, this is the integral which I have here. Okay, so now I want to change it to the base. Okay, here this is del b tilde x tilde t. So you see, for us, okay, for us this g tilde, okay, if you think about it, this g tilde is independent of the third variable, right? Yes or no? I mean, just think about it for a moment. If you want, you can pause the video, think about it, what I am saying, that you see that g tilde does not depend on y3, right? So, since, let me write it like this, g tilde does not depend on y3, okay, it does not depends on y3, okay. So now, of course, what is y? So this is with respect to y, okay, ds y tilde. So I'm not writing all that. I hope you guys understood, okay. This I'm not writing. So see, y is here. So y is with respect to, y is on the boundary of the ball, okay. So I'm not writing all that. I mean, that is fine. So y is y1, y2, y3. So g tilde does not depends on y3. Clear? Okay. So if it does not depends on y3, then, because you see g tilde x1, x2, x3. So I mean, if you replace it by y1, y2, y3, so basically that is independent of the third variable. Okay. So the g tilde does not depends on y3. Okay. If it does not depends on y3, then this integral. Okay. So basically, you see this particular thing, you can break it up into two hemisphere, the upper hemisphere and the lower hemisphere. Yes, you can break it up into two hemispheres. Okay. So from 3, what I can write is this. I will write it as 2 times this particular term, integral. It's not on the boundary of del b tilde, but now it will be on the base for x3 equals to 0. Okay. So let me write it from 3. From 3 we have then del b tilde x tilde t, okay, g tilde ds tilde, okay. I mean, if you want, you can write it as y, but I mean, that is given. Yeah, if you want, you write it as g tilde of y ds tilde. I'm not writing all that. Okay, that's fine. So this is given by, okay, so 2 by 4 pi t square. Why 2 is coming? Because of the two upper half, one half and other half. G tilde is independent of y3. So basically, you in both half, it's I mean, its contribution is same. Okay. So it is 2 by 4 pi t square integral over the ball bxt. Yeah, I can write it like this. See, I mean, here S is getting converted to D. D is this region. This is the whole region. S is the surface here. Okay. So if del B x tilde T, okay, when you are working with this thing, where will it convert? It will convert to the this whole thing, the base for x3 equals to 0, the whole thing inside, whatever is inside, right? Okay. So that is why it becomes B of xt. Okay, and of course you have g of y, okay, and then this calculation is there, px square plus py square. Okay. I wrote it in a, sorry, this is a confusing thing. Yeah, let me write it like this, p of x1 x2 p of x2 square. Clear? Okay. Sorry, I mean, there are a lot of variables involved, right? So I mean, just to make all of this more precise, that is why this confusion is happening. Okay, I hope this is fine. Yes. Okay, so you see this particular term, the scaling term px1 square plus px2 square plus 1, in our case, what is the graph of the function? So basically that is given by t square minus equals to the boundary, t square equals to x minus y square, right? Okay, so basically now if you calculate this thing, so please do it yourself. You get a extra term. What is the extra term? The extra term is 1 plus gradient, how do I put it, gamma y square whole power of half dy. Clear? Where gamma of y is equals to t square minus y minus x square whole power half. Okay, for y in bxt. Clear? Okay, I mean, I'm just writing the surface. This is the surface of the sphere. Here this p is getting replaced with the surface of the sphere, and then I'm just calculating px square plus py square. So this is gradient of p square, plus 1. You see, this is what I calculated. Okay, whole power half. Okay, so that is what I just calculated and just wrote it there. I mean nothing special. And of course, again, y2 is coming because you know, it consists of the two hemispheres, right? So just to accommodate that, we have this. Now you see, since 1 plus gradient gamma y, the square of that, okay, whole power half, that if you calculate it, it is t times t square minus y minus x square whole power minus half. Clear? Okay, I mean, of course you can check this part, but there is nothing to check. I mean, this is just a calculation. Okay, nothing much is there. So therefore what we have is the average of g tilde on this b tilde x tilde t g tilde, okay, ds tilde. This is given by 1 by 2 pi t, right? Because you know that is getting cancelled, and this t and this t square is getting cancelled, and you have b of xt g of y by t square minus y minus x square whole power half dy. Clear? I mean, just you know, you just put the values of this in here, and that is what we are going to get, right? I mean, this thing I'm just putting it here. Okay, now if you do that, then now what happens is this, you know, so if I write it like, you know, the how can I say, the average, then it will happen that it will become t by 2, because you know the volume of the ball will be included, so it get some terms get cancelled out and it will become t by 2, and then the average of bxt, okay, g of y by t square minus y minus x square whole power half dy. Clear? Whole power half dy. Now you see, hence therefore what do you have? U of xt. How does it look like? U of xt, you remember this formula, right? So this is this g tilde integral, the average of g tilde is this, yes, and u of xt is given like this. U of xt is this, so I will just put that average of g tilde in here, okay, and then what I have is u of xt is half of del t, clear, of t square, because already one t is there and this t part is there, so t square, okay, t square, this half is coming from here, this t by 2, that is why this half is there, okay, t square, and yeah, the average of bxt, where is it, yeah, g of y by t square minus y minus x whole power, sorry, square whole power half, okay, dy, fine, plus t square by 2 bxt, the h part, so this is h of y by t square. How is this coming? You know, the exact same thing, yeah, so this I am skipping this part, okay, t square minus y minus x square whole power half, okay, d of y. How this is coming? Again, the same exact same sort of procedure will work here, yes. Okay, so I mean you just replace g tilde with h tilde and the same thing happens. Okay, now see this t square, the average on bxt of g of y by t square minus mod y minus x square whole power half. Okay, this dy, if you change the variable here, this will look like t times b01. Okay, you remember the change of variable which we always use, tz by 1 minus mod z square whole power half dz. Clear? And so what do you have? We have this one, this calculation del t. So I have to calculate this del t, right, of t square bxt gy by t square minus y minus x square whole power half dy. Clear? This is equals to the average on b01 g of x plus tz, clear, by 1 minus mod z square whole power half. I am just writing whatever is there. I mean, I am not the exact same thing I am just writing. Dz plus t times from here, sorry, not from here, from here, t times b, the boundary, sorry, the ball b01 gradient g of x plus tz dot z by 1 minus mod z square whole power half dz. Yes, I hope this is clear. I mean, I'm not doing anything except that, you know, I'm just calculating the derivative. That's it. Yeah? So I'm just calculating the derivative. I'm just putting it there and writing it down, right? So I hope that I hope I do not have to explain you this particular. I mean, this is trivial. Yes, just do the Lipschitz formula thing and it's done. So this is given by t times b xt, okay, g of y by t square minus y minus x square. So I will just write it together properly. Yeah? D of y plus t times integral bxt, okay, gradient of gy dot y minus x by t square minus y minus x square whole power half dy. Okay, I mean, you just put everything together in terms of y and x. Okay, now we are at the end of the formula, but I mean, we have to go to the, therefore, what is u of xt? Now let us write down what the the ultimate formula is. This is half. Okay, so I'm just putting everything together. Yes, I'm not calculating because it will become more big. So let me put everything together. So if you are not convinced, please do it yourself. I mean, there is nothing to do. You have this thing, you just put it together with this h, that's all. Okay, and so this is t g of y plus t square h of y plus t gradient g of y dot y minus x by t square minus y minus x square whole power half dy. Clear? So this holds for x in R2 and T of course positive. Clear? This formula, so let's call it a star. Star is called the Poisson formula for the solution of one in two dimension. Clear? Okay. So see, so let me explain to you what we did again. Again, see, I know how to work with three-dimensional wave equation, right? That we know. So three-dimensional wave equation, last class we did. There is a Kirchhoff's formula which actually deals with three-dimensional wave equation. Two-dimensional wave equation, what we are doing is we are writing this we are defining a new function which is a three-dimensional function, of course, for a fixed time three-dimensional function, and that is defined by this two-dimensional u. This is of course assuming that there is a solution u. Okay, now how do you know that there is a solution? Of course there is a solution, that is Cauchy-Kovalevsky theorem. Okay, but we are not going to delve into that for now. Let us assume that there is a solution. If there is a solution, it will look like what? That is what our question is. So u tilde is given by u. Now this is Hadamard's method of descent. So we are using this trick of going from n equals to 3 to 2. So once you use that trick, okay, you write this equation in terms of u tilde, equation 2. Okay, you know what is the formula for equation 2. The formula is given by this. Yes. Once you know this thing, what you do is you just calculate what t times g tilde ds is. Okay, for that you need some surface integral. Use the surface integral, write down what this particular thing is, that what is the average of g tilde, that is this, and once you do that, you have u of xt which will look like this if you put it in that formula, right? Now you do not have to do anything but just calculate what is del t of t square, the average, this particular thing you just have to calculate. Once we calculate this thing, put everything together and you have u of xt. So it is not very difficult, it's just a tedious calculations. Okay, now, okay, so this is fine. This is what we called a Poisson. So please remember that the other formula for n equals to 3. So for n equals to 3, it is called the Kirchhoff formula. And for n equals to 2, it's called the Poisson formula. Okay, now we are going to use similar thing for higher dimension, but that we'll do it in next week. Clear? So after this, what we are going to do is, so here we did the homogeneous problem, right? So now what we will do is the inhomogeneous problem. The new section is the inhomogeneous Cauchy problem, right? So what is the inhomogeneous Cauchy problem? It is basically the D'Alembert of u is given by capital F. Yes. So let's call it I don't know, maybe up till here what did we say? It is 3, right? Let's call it a 4. Okay, this is the problem given to us, and of course you have this boundary condition. The initial condition is there, u is equals to g and u tilde is equals to h. Yeah, those boundary conditions are there in whatever the region is. Yeah, see, now I will assume that I know how to handle the homogeneous problem in any dimension. Although I don't know that, I know only for n equals to 3 and n equals to 2. Higher dimension we will do because that is very, very complicated, higher dimension. Okay, we will do in the next class, but for now I will just assume that let's assume that we know this. Yeah, but at least you can of course assume that n equals to 2 and 3 we already know. Yeah, 1, 2, 3 1 is the D'Alembert's formula, 2 is the Poisson's formula, 3 is the Kirchhoff's formula, right? So all of these 3 we know. Now from there I want to find out what the inhomogeneous Cauchy problem, can we solve that? Yeah. So this is the problem. Let's call this 4. So this is like Rn, let's say, cross t equals to 0. Okay, so n can be here, let's say n can be any number n, so n can be 1, 2, 3, 4, whatever here. Okay, we are assuming that we know how to solve the homogeneous problem, and from there we'll do this thing. Yeah, this will work for anything. Okay, so let's do that. You remember in heat what we did for this kind of problem? We used Duhamel's principle. Here also we are going to do something like that. So before doing that, let's see something superposition. Okay, see the equation, the D'Alembertian of U equals to F is a linear equation, right? Is a linear equation. Of course, it's a linear equation, and the same holds for heat equation also. It's a linear equation, right? Okay, so you can actually separate out two parts. So basically, you can write u of xt to be u1 of xt plus u2 of xt. Clear? Okay, where the D'Alembertian of u1 of xt, that is given by that is 0. Okay, with u at the point x0 is f of g of x, let's say g of x, ut at the point x0 is h of x. Okay, and the D'Alembertian of u1 of xt, that is going to be capital F. Okay, u at the point x0, u1 sorry, this is u2, u2 at the point x0, this is going to be 0, and u, okay, u2 with respect to t, I think this is fine. Yeah, okay, x0, this is equals to 0. Okay, I don't want to write it u2 t, that will get confusing. So basically ut with respect to t at the point x0, that is going to be 0. So you see, if u1 and u2 solve these two problems, then if you add, so this is u1, this is u1, with respect to t. Let me write it properly. So basically u1 with respect to t. Okay, and here also u1. So you see, if u1 and u2 u1 solves this problem and u2 solves this problem, if you add those two up, because of the linearity, the D'Alembertian of u1 plus u2 is f, and u1 at the point x0 is g, u. So basically, if you add it up, what will happen? The D'Alembertian of u is 0. Okay, the u is equals to g, because g plus 0 is 0. So at x equals to 0, and ut, that is going to be h, right? Okay, so we broke it up into two parts. Now, what about the first part? So let's say this is your 5 and that's your 6. Okay, so the 5 part you already know. This is a homogeneous problem. Okay, so this is a homogeneous wave equation. Okay, we know what to do with this. Plus, this is a inhomogeneous wave equation. But at least some good news is it has a homogeneous boundary condition. Clear? Okay, so what we are going to do is, let's say that for now, let's just assume g and h is 0. Yeah, I mean, that's not a issue here. Okay, so assume, of course, g and h is 0, I mean, you can actually solve the problem, right? Yes. So I will denote it like this: w, okay, wave, because of the wave equation, w, f of xt s. You remember that s, yeah, the solution of the homogeneous problem. Now I am using Duhamel. You remember Duhamel? What did Duhamel do? Duhamel, it said that if you have an inhomogeneous problem, okay, you solve a bunch of homogeneous problems and then sum it up, right? So integrate it. So that is what we are doing here. So we wrote so let WF, capital F of XTS be the solution of the homogeneous problem. Which homogeneous problem? The D'Alembertian of W is 0 and W at the t equals to S, that level, this is 0, and WT with respect to W with respect to time variable t at t equals to S, that is given by capital F of XS. Okay, so basically the source term capital F in this is getting converted to the boundary here F. Okay, so we are basically saying on the boundary F is S. So for S equals to t equals to S, actually for every level t equals to S, this is given by capital F. Okay, so in n dimension, let's do it in n dimension, then we can go from there, right? Okay, so you see, for n equals to 3 we have this Kirchhoff formula. Yes, for n equals to 3 we have this Kirchhoff formula. So we are going to use this formula, we are going to use this formula, and we are going to find what the solution is. So now what we are going to do is, you see, this we know how to solve. Yes, I mean whatever the dimension is, let's say. Yeah, so this is, let's say, in Rn cross 0 infinity, right? Duhamel's principle says that if you write, let's say, u of xt, okay, this is equals to, so I am defining it, 0 to t wf of xt s ds. Okay, if you define it like this, okay, then so this is for x in Rn and t greater than equal 0. If you define it like this, then it says that this is the solution of, let me write it here, utt. So basically the D'Alembertian of u equals to capital F, okay, in Rn cross 0 infinity, and u is equals to 0, ut this is equals to 0 on Rn cross t equals to 0, right? So is it clear? To the problem 4, actually, to the problem 4. Okay, so see, these 5, I know how to solve 5, right? I mean, for now, at least for n equals to 1, 2, 3, I know how to solve 5, and the problem 6 only is a huge problem for us. So to deal with that, what we are doing is, we are saying that, let's say, we know what is the solution of this homogeneous problem. Okay, of course we know what is the solution of this homogeneous problem, at least for n equals to 1, 2, 3 for now. Okay, what does Duhamel's principle says? That if you write u to be the integral of wf, right? So you solve the homogeneous problem at the level t equals to s, and then integrate between 0 and t. If you define u like that, then that u will solve this problem, right? Which problem is it? It is basically the 6th problem. Clear? If you know what 5 is, you know what 6 is. If you add it up, then you have your solution. Clear? Okay. So let me write down the theorem, okay, and then we'll go from there. So theorem 4. Theorem for non-homogeneous problem. So basically, let's write it like the non-homogeneous wave equation. Homogeneous wave equation. Okay. So assume n is greater than equal to, and f belongs to the capital F belongs to C, the box function of n by 2 plus 1, okay, Rn cross 0 infinity open, okay, and define u as as this one. How do I put it? How do I put it? Maybe star I already used somewhere, right? Star I have used for the Poisson formula. So let's call it double star maybe. Yeah, double star. So basically, let's U is defined by U defined as double star. Okay. Then you have the following. Number A, U is in C2 of Rn cross 0 infinity. Okay, please realize this thing. I am taking a liberty of assuming that I know that how to solve the homogeneous problem for every dimension. I don't know that. Up till now, I did only for n equals to 2 and 3, but I am assuming that we know. Exactly the same sort of thing will happen, but it will be more complicated. Okay, we'll do it next week. So, but I am assuming that for now. So, once you do that, you see, we can do all of this, whatever I am doing here. Okay, so U is in C2. Okay, so basically, if you take capital F to be in C, the box of n by 2. So, basically, let's say n equals to 3. Yeah, so in that case, it is 2. C2 of Rn cross 0 infinity. So then U is also in C2, and moreover the D'Alembertian of U, this is going to be capital F, yeah, in Rn cross 0 infinity. Okay, and C is limit. Okay, see, boundary condition is given like this: xt going to x naught 0. Okay, and x is in Rn, t positive, U of xt, that is 0. Okay, limit again same thing, xt going to x naught 0, x is in Rn, t positive, ut of xt, that is 0. Okay, for each point x naught in Rn. Clear? Okay. So this is the theorem which I have. So basically what it is saying is, if you want a non-homogeneous wave equation, if you want a solution of non-homogeneous wave equation, that is given by this U. What is this U? U is given by this, the integral of Wf, where Wf solves this problem. Okay, and what is the total solution? U of xt will look like U1 plus U2, where U1 is the solution of the homogeneous part with G and H, and U2 is the solution of the inhomogeneous part with 0 initial condition. Clear? Okay, so so this theorem says that if you take capital F to be in C2, U is also in C2. U solves the the wave equation in non-homogeneous or inhomogeneous wave equation, and on the boundary U tends towards 0. Okay, so let's look at the proof of this thing. Proof. See, first of all, if n is odd, okay, then n by 2 plus 1, the box function of n by 2 plus 1, that is given by, of course, n plus 1 by 2. I mean, yeah, that's fine. Okay, so therefore, what you have is, if C, if capital F, so therefore, if capital F is in C 2 of C n plus 1, okay, by 2, okay, n is odd, capital F is in C n plus 1 by 2. So basically, let's say n equals to 3. Okay, so in that case, it will be 2. So capital F is in C2, let's say C2, okay, of course, Rn cross close 0 infinity open. Okay, then that the function which you got, I mean W of f, see, Wf of xts, if capital F is in C2, okay, this problem is in C2, that is clear, right? Wf is in C2. Why? You see, Wf is a homogeneous problem, right? I mean, let's say n equals to 3, right? I took n equals to 3 from Kirchhoff's formula. I mean, if you look at, so this is a small exercise. Okay, check using Kirchhoff's formula for n equals to 3. Okay, this one, whatever I am writing, that if f is in C2, n equals to 3, f is in C2, then the Wf which you are getting, this we will get for n equals to 3, you will get using Kirchhoff's formula, right? Okay, the Wf which you are getting, this Wf is the solution of this problem, right? Wf is the solution of this problem. Okay, for each s positive is in C2, then capital Wf x t s, okay, that is in C2 of Rn cross S infinity, okay, for each s greater than equal 0. Clear? And hence W u, which is defined by the integral of Wf, you see u is defined by the integral of Wf between 0 and t, right? Okay, so if Wf is in C2, u is of course at least actually C3, but I mean for now you can of course take it to be C2, that's not a issue, right? Okay, so hence u is in C2 of Rn cross 0 infinity. Clear? If n is even, then n by 2 plus 1 is n plus 2 by 2. Clear? Okay, and again the same thing in the for the Kirchhoff, here it will be a Kirchhoff formula for n equals to 3. You can take the Poisson here and you can show that if n is even, then n plus 2 by 1, the box of n plus 2 plus 1 is n plus 2 by 2, and since capital F is in C n plus 2 by 2, okay, so let's say n equals to 2, this is also C, F is in C2, right? So if F is in C2, that will imply U is in C2, the same sort of logic will work, right? Okay, so U is in C2 of Rn cross 0 infinity open. Clear? Okay, say exact same sort of logic. I mean, you can think of this using Poisson. Of this using Poisson formula. Clear? Okay, so this you guys have to do it yourself. I mean, there is nothing much to do, guys. So please check this part. Right now, so this is the first part gone. A. Now, what about B? B is not a very difficult thing to check. You see, ut of xt, if you take, that is essentially Wf of xt t s equals to t, okay, plus 0 to t Wf with respect to t at x t s ds, right? Yes. Do you think this is true? Of course, this is why I am just doing differentiation with respect to the integral sign. Yes. So this is the boundary term. This is 0 to t. This term is there here, and then this is given by 0 to t Wf with respect to t at the point x t s ds. Okay. Right now. And what is utt of x comma t? That is given by ut. Again, I am just taking the derivative again. I mean, again I am doing the derivative. I mean, differentiation on the integral sign. Okay. Okay. I did explain last. This is 0, right? This is 0. So basically, this becomes this, and then now I want to write utt. Then I have to differentiate this thing with respect to time. Okay. So same kind of thing will happen. Ut of Wf with respect to t of x t plus 0 to t Wf with respect to tt of x t s ds. Okay, so that is equals to f of xt, capital F of xt, okay, plus, let me write it properly. So I think this is clear. Yeah? I'm not doing anything, but I'm just doing this thing, differentiation under the sign of integration. Clear? I'm just using this thing in both the cases. Yes, in both the cases I'm just using this part, that's all. Okay, yeah, where am I? utt is this, right? Okay, so yeah, this is fine, okay. And now you see ut of xtt. Yes, if you remember what is this thing wft with xtt, yeah, for s equals to t. wf is 0 for s equals to t. If you see, wf is a solution, right? Okay, so w is 0, okay, and wt is capital F, okay. So that is why this wf is 0, I do not have that. Wf is capital F, so this is capital F of xt plus 0 to t wf, okay, with respect to, so this is not with respect to f, this is just a notation wf. This is basically the solution w with when we have the initial condition as f, capital F, okay, with respect to tt at the point xt s ds. Clear? Okay, right. Also Laplacian of u xt, okay, what is it? This is nothing but 0 to t Laplacian of u xt s ds, right? Why? Because you know this integral is with respect to time variable and I am doing the differentiation with respect to the spatial variable, so I can just take it inside and this is what I have. And that again, see here, see u is this, right? So if you take Laplacian of u, it becomes Laplacian of wf, right? Laplacian of wf is basically, this is what? The D'Alembert of w is wtt minus Laplacian of w, right? So Laplacian of wf minus wf with respect to double derivative tt minus the Laplacian of wf, that is 0, right? That is given to us. So here you see this, I have to change it a little bit. So this will be Laplacian of wf at the point xt s. Clear? Okay, so this is given by 0 to t, and since wf solves the D'Alembertian, it is wf with respect to tt, okay, xt s ds. Clear? Okay, now you see if you take utt minus this, so basically you have f of xt. Okay, so I am not writing that thing, I guess this is fine. Yeah. What about the initial conditions? Initial conditions also there is nothing special. Of course, you can see that if you define w, capital U like wf, since w on the boundary, initially it is 0. Okay, so you can actually have this the c part, this and this. So u is defined by integral of wf from 0 to t. Okay, so at t equals to 0, you do understand as t approaches 0, this integral becomes from 0 to 0 this, which is 0, and the same holds for ut also. Okay, so ut is given by, you see what is ut is given by this. Okay, now as t tends to 0, you do realize that this is going to 0, right? So there is nothing else to prove, I am just leaving it to you, so please do it yourself. Okay, right. Now I have another small details to work out. Okay, so this is for n greater than equal to. I hope this is fine. See this thing, what does it do? You have using this theorem, we solved what 4 is. Yeah, 5 we already know via Kirchhoff and Poisson. Now if you want to find a u, what you do, you just take those two and put it together. Okay, it is going to be a very extremely big and complicated formula, but you have the exact equation, right? Clear? So that is there. Now so this is for n greater than equal to, if you remember. Yeah, now let us do it for n equals to 1. Okay, for the case n equals to 1, n equals to 1. Okay, so what does D'Alembert's formula gives us? You see, in this case, u of I mean, if you use D'Alembert here, okay, u, so okay, one small thing I need to do here. You see, the equation here, it should look like this, no, utt minus uxx equals to small f. So this is the problem I need to solve in one dimension. Yes, r cross 0 infinity and u equals to 0, ut is equals to 0 on r cross t equals to 0. Okay, so you see the exact Duhamel's principle, everything works fine. So from Duhamel's principle, of course, from D'Alembert, first of all, yeah, so you realize that if I want to solve this problem, what do I do? I first of all find out solution of this. So let's say, I mean, you remember, I don't know what did I put it here. I mean, what is the last number? There are so many numbers. Sorry, this is 5. 5 is the last one. Or 6? I thought I put somewhere 6. No. So anyways, let's call it as the problem P. That will be better. Yeah. So let's say I want to solve this problem P. Now you know that the exact same thing which we did for this case, this case, the problem P can be divided into two parts, 4 and 5. Exactly like this we can do it. Yes or no? Yeah, you can do this part. Yeah, once you do this part, so exactly what am I trying to say? Let me write it properly, and then maybe it will be a little less confusion. Okay, so let's say this is G, that is H. Yeah, if I have to solve this problem P, I can break it up into two parts. Okay, so this problem can be broken up into two parts. One part is this u, so D'Alembertian of u is equals to f. Okay, u is equals to 0, ut is equals to 0, one part. Okay, the second part is D'Alembertian of u is equals to 0, u is equals to g, and ut is equals to h. Clear? Okay, I can do this. Now you see, this problem, of course, by D'Alembert's formula I know. So let's call it P1, and let's call this thing as P2. Okay, now you see P1, P2 I know how to solve it. Okay, so we know how to solve P2. Okay, using D'Alembert's formula. My only concern is how do I find P1. Okay, now you see what I am going to do is P2, we can just write it, I mean, you just think of this as at the point x s, right? So I will use Duhamel's principle essentially, but I mean, what I am going to do is I am going to write it like this. So basically, let me do it here. U of x t comma s, u basically this is your wf, that if you want to write it from D'Alembert's, yeah. So essentially this problem for the time t equals to s, you understand, P2 for t equals to s if you want to write. So basically if I want to solve this P1, so I can solve P2 for t equals to s, right? Yeah, and then go from there. So I'm going to do something like this. I hope you are understanding what I'm trying to say. See, I want to solve this problem. So basically WF, that the WF solution what we did, that problem I want to solve. So essentially this problem I want to solve, but for one dimension. Yeah, this problem I want to solve for one dimension. Is this clear? Okay, and then I mean, what is the solution of that problem? I can use D'Alembert's formula. Is this clear? Okay, so let me use the D'Alembert formula. So let me write down this problem. Let's call this problem as the MP. Okay, so let's say that what am I doing here? Yeah, so u of xts, this is the solution for MP for n equals to 1. So MP n equals to 1, n equals to, you take n equals to 1, and u is the solution of MP for n equals to 1. And how does it look like? By D'Alembert formula, it will look like x minus t plus s, x plus t minus s, f of ys dy. Is this clear? Okay, so where u of x t comma s is the solution of MP okay, for n equals to 1. Clear? Okay, I wanted to write that equation, that is why it was a little confusing. So there are, you do understand that each dimension has to be dealt with differently, that is why there is a little confusion, but I hope this is fine. Yes, now if you do that, therefore by Duhamel, so this is by D'Alembert, yeah, D'Alembert, yeah. Now by Duhamel's principle, what do you have? Principle, we have that u of xt, you can write it as half t, s will lie between 0 and t, right, and then you have y riding between x minus s plus s, x plus t minus s, f of ys dy ds. So basically this thing, and after that you take s to from 0 to t, that is Duhamel's principle, that is your u of xt. If you define u of xt like this, then I mean exactly the same thing which we did, you can show that this is actually the solution of the problem. So basically you can write it in a nice way like this: u of xt is half 0 to t, okay, x minus s to x plus f, f of y t minus s dy ds. This is for x in R and t positive. So this is just a change of variable. So is this clear what I am saying? See, I will solve the problem MP for n equals to 1. Yes, let us assume that the solution is given by u for the time t equals to s, and that is given by this. How do I know that? That is D'Alembert's formula. Yes, I use D'Alembert's formula for the level t equals to s. Okay, once I have that, then you use the Duhamel's principle to get what u of xt is. Clear? Once you have u of xt, I mean, you can of course prove that this u solves the problem. Yeah, and this I am not doing because this will be again the same sort of thing. Yeah, nothing changes. The same sort of calculation will work, whatever we did for higher dimension. Just a little easy. And then what happens is you just use a change of variable and write it like this. So this is the formula which you have for one dimension. Okay, I mean this is the solution for one dimensional equation. This thing P1. This is the formula for P1. Okay, so yeah, this is the formula for P1. Clear? Okay. So with this we are going to end this lecture.